Hi, I'm Jannis Hoffmann. I'm a mechanical engineering student from the University of Applied Sciences Bremen in Germany, and this is my entry into the Altair Global Student Contest. I'm not only a fan of structural optimization and analysis, but also I'm a 3D printer enthusiast. And this is a CoreXY 3D printer that I built approximately 2 years ago. And as part of my entry, I wanted to check whether such a 3D printer design could actually be optimized. Now we can dive deeper into how such a CoreXY-robot actually works. It has a toolhead which moves in 2 axes, and it has 2 motors which run on separate belt loops with some pulleys and idlers. And if you turn one motor in one direction, the toolhead will move diagonally. If you turn both motors in the same direction, it will move left and right. And if you turn them in opposite directions, it will move front to back. Here you can see the CAD model that I created of a similar CoreXY robot. It consists of a frame and moving components itself. After import, I set up all of the rigid groups, joints, and fasteners of the model, which Inspire handled mostly automatically. Now that we know how a CoreXY kinematic actually works, we'll need to come up with a realistic load set that respects the rules of the kinematic. To do this, I substituted each and every one of these little belt pieces right here with 2 force actuators. One which simulates the constant preload force, which is always applied, and the other one which basically simulates a varying torque of the motor. Now, if you do the math, a total of 24 actuators needs to be created, because 12 belt pieces need to be substituted, and each one of them needs to be substituted with 1 constant preload actuator and 1 varying actuator which represents the motor torque. And this can be quite a hassle to do manually, because each one of them needs a value and a frequency and stuff like that. So I set up a bit of Python script which interfaces with the Python API of Inspire, and I basically give it frequency settings for both motors, maximum motor torques, and phase shifts for the 2 motors. And out of these pieces of information, it automatically sets up all 24 actuators in the model with all correct values, which was a huge time saver and a lot of fun to program. We'll also need to validate our motion model that we created. In order to do that, I at first only used the preload actuators, which all have the same constant force, and ran a motion analysis, and if everything would go correctly, nothing would move, which it does now. You can see nothing moves. And luckily the simulations showed the same, so that was quite a nice validation of the created motion setup. I tried a couple of different ways to simulate the varying motor torques, and in the end I decided to use an oscillating force actuator, which basically simulates that each motor turns into both directions or applies torques in varying directions with a given frequency. And these 2 frequencies between the 2 motors don't actually match up, so because of this there are a bunch of different combinations of motor torques under which the system is tested. Now we'll need to answer the question what to optimize and why. I want to do a topology optimization in order to decrease mass, but for 2 different reasons. One is to actually decrease the mass of the 3D printer, so we'll need to get a big absolute weight reduction on this. The other one is to decrease moving masses on the printhead and the motion system in order to increase dynamics, so we'll need to get a relatively large, but in absolute values quite small, amount of weight reduction on these moving parts. Before now using the results of the motion analysis we created for the optimizer itself, I needed to partition the model in order to correctly define the design spaces so that the optimizer doesn't try to optimize the interface points between two different parts. Here's the weight we saved through optimizing in all of the moving components. As you can see, the absolute numbers are not that big, but the relative numbers are quite substantial. And if we go to the weight we saved within the frame, we can see that we saved about 8 kilograms, which is quite substantial. Of course, I then repeated the motion analysis with the optimized parts in order to get loads for a static analysis, which then showed that all of the stresses and displacements were within realistic bounds of the material and the use case, and even indicated that some further weight savings might theoretically be possible. So now, after the structural optimization itself is actually finished, we'll need to answer the most tricky question, which is, can you actually manufacture these parts? For the side panels, I think this is fairly easy. It should be pretty doable to just laser cut them from acrylic or something similar. And for the moving parts, I mean, they do look quite complex, so I tried to 3D print them on another desktop FDM 3D printer, and they came out very nice. So these are the side parts, the left and right sliders, and they, I think, came out very nicely without any issues. So yeah, thank you for watching. It's been a pleasure.